Today we are going to evaluate this limit. The limit is limit x approaching infinity of x plus 2 over x minus 2, and it is being raised to power x. So as we can see that we are interested in finding what this expression approaches when x approaches infinity. So what does this x approaching infinity mean? So x approaching infinity means that x is becoming very large. How large? We don't know, because infinity is not a number. And if we just know that infinity is a very large number, and when we add 2 to a very large number, it remains a very large number, so the numerator will be infinity. And when we subtract 2 from a very large positive number, it will still remain a very large positive number, so the denominator will also be infinity. And as I've said, that we don't know how large is this infinity. We don't know what infinity is. Infinity is just used to indicate that a number is getting very large. That is pretty vague. So as infinity is not a fixed number, not a definite number, so we can't really divide, because division needs two real numbers. Like, for example, 1 over 4. We are dividing 1 by 4. 1 and 4 are two real numbers, and they can be divided. But infinity is not a number. So we can't divide infinity by infinity. We can't evaluate infinity by infinity. So this is undefined, and this is an indeterminate form. So we need to get rid of this form to evaluate this limit. And what we can do is, if you look at the expression is x plus 2 over x minus 2, and we can see that this is an improper fraction. The degree in the numerator and the degree in the denominator, they are equal, so we can divide it. We can use long division here. So we are dividing x plus 2 by x minus 2. So x minus 2, if multiplied by 1, is x minus 2, and in division we subtract what we get by multiplying. So we got x minus 2 when we did multiplication, so we are going to subtract it from x plus 2, and subtraction changes signs. So plus will be minus, and minus will change into positive. So x and negative x, they get cancelled, and we are left with 2 plus 2, which is 4. So now we can write our given fraction in this form. X plus 2 divided by x minus 2 can be written as 1 plus 4 over x minus 2. This is same as saying, for example, we had 7 divided by 2. If we divide 7 by 2, we get a remainder, which is 1, because 2 3s is 6, and we have a remainder 1. So we can write 7 by 2 as 3 whole 1 over 2 as a mixed number, and this indeed can be written as 3 plus 1 over 2. So similarly, we had x plus 2 over x minus 2. We can write it as this, 1 whole 4 over x minus 2. Looks weird. which can be written as 1 plus 4 over x minus 2. This side number is basically the your quotient, and the numerator written here 1 is the remainder, and this was your divisor. So we can write our given fraction as this 1 plus 4 over x minus 2. So I've written our given fraction as 1 plus 4 over x minus 2. And when we do that, we get limit x approaching infinity of 1 plus 4 over x minus 2. Mind you, this infinity is positive infinity, meaning x is getting very, very large in positive direction. So we have a result which is that if you take limit of 1 plus a over x, and that is being raised to power x, this is equal to e raised to power a, and this is true when x is approaching infinity, positive infinity. So here, if you notice, in our given limit, we have 1 plus a form, if you notice this result, in this we have 1 plus something written, a fraction. The denominator of that fraction and the power of this whole expression, they are same. X is approaching infinity, and the result is e, which is Euler's number. It's an irrational number, 2.7818 up to so on, and it is being raised to the number written over here in the numerator of the fraction, e raised to power a. So how can we use this result to evaluate this limit? If we notice, if you look at this limit, x is approaching infinity, that is fine. We have 1 plus also in our given limit, and we have a number, a is 4, and we have a denominator which is x minus 2, but there's a problem here. We don't have the same denominator and power. The denominator is x minus 2 and the power is x. In order for us to use this result, this denominator and this power, they need to be same. And the example of this result is, this is a well-known limit, that limit as x approaches infinity of 1 plus 1 over x raised to power x is equal to e, and here a, you can see it is 1, so e raised to power 1, which is just e. So this limit is equal to e. This is a well-known result, and the general result is this, which we are going to use in order to evaluate our limit, this limit. So as I said, that the denominator and the power need to be same for us to use this result. So we need to make this x minus 2. And how can we do that? We can write this as 1 plus 4 over x minus 2 raised to power x minus 2 times 1 plus 4 over x minus 2 whole squared, because when the bases are same, the powers are added, and when we add x minus 2 and plus 2, we get x, because minus 2 and plus 2, they cancel out. So we indeed get what is our required limit, 1 plus 4 over x minus 2 raised to power x. So we can write our limit in this form, and we did this because we wanted to use the result. And now a single limit is being applied to a product, and the rule of the limits tells us that this can be written as the product of two separate limits. So limit approaching x approaching infinity of 1 plus 4 over x minus 2 raised to power x minus 2 times limit x is approaching infinity of 1 plus 4 over x minus 2 whole squared. So this, resembles our result now, because the denominator and the power are same. We have a, which is 4 here, x is approaching infinity, and we have 1 plus a fraction. So what's the result of this limit? This is simply equal to e raised to power a. So e raised to power a is e raised to power 4, because a is 4. So this is e raised to power 4, and we need to evaluate this limit so that we can evaluate what we want to evaluate. So here we have x only in this term. X is approaching infinity, meaning x is a very large positive number, or is getting very large. So that means that subtracting 2 from it won't make any difference. So this will be a very large number, and 4 divided by a very large positive number, this approaches 0. So 1 plus 0 is 1, and 1 squared is simply 1. So this limit is approaching 1, and this is equal to e raised to power 4. So e raised to power 4 into 1 is e raised to power 4, and here e is 2.7818, Euler's number. So our limit is equal to e raised to power 4. Now the only thing which we want to verify is that this result is true, this result which we use to evaluate our limit. Limit x approaching infinity of 1 plus a over x raised to power x is equal to e raised to power a. We need to prove this. So I was saying that we need to prove this result, and I'm going to prove this by letting a is equal to 1 as first example, and I'm going to take a is equal to 2 for the second example, and you will see that both of those limits will be equal to e raised to power a, whatever the a in that case is. So I'm taking a is equal to 1 firstly, and when we take a is equal to 1, we have the limit x approaching positive infinity of 1 plus 1 over x raised to power x. So how can we evaluate this limit? This thing basically, this can be expanded using binomial series, and the binomial series is 1 plus x, whatever written here as second term is basically our x. So 1 plus x raised to power n is equal to 1 plus n is the power. So 1 plus nx plus n into n minus 1 over 2 factorial x squared up to so on. So here we have 1 over x in place of x and x in place of n. So 1 plus n, which is x, into the second term, which is 1 over x, plus n, which is our power, which is x, into n minus 1, x minus 1 over 2 factorial, times the second term squared, which is 1 over x, so 1 over x squared, plus n, which is x, into n minus 1 into n minus 2 over 3 factorial, times the second term cubed, 1 over x whole cubed, up to so on. This goes on and on. So we can simplify this expansion and apply this limit to those terms separately. So this x and x, they get cancelled. So we are left with 1 plus 1 plus 2 factorial is simply 2, because 2 factorial is equal to 2 into 1, so which is 2. 1 over x squared is 1 over x squared. So x and 1x from this x squared, they get cancelled. Similarly, if we simplify this term, we are left with x into x minus 1 into x minus 2 over 3 factorial, which is 3 into 2 into 1, which is 6 of 1 over x cube. So x and this x cube, 1x from this x cube, they get cancelled. So we are left with 2 plus x minus 1 over 2x plus x minus 1 times x minus 2 over 6x squared up to so on. So the first term doesn't involve x, so this will remain 2 after applying the limit. So this is 2. The second term is x minus 1 over 2x. Currently, if we put infinity into this, this will remain infinity over infinity. So we need to simplify this. So there are two terms in the numerator. They can be written as x over 2x minus 1 over 2x, because if we take the LCM of this thing, we get the same thing. X and x, they get cancelled. Similarly, we can multiply these two factors in the numerator. We get x squared minus 3x plus 2 over 6x squared, and we will apply the same thing. We'll do the same thing here. We will distribute this denominator on these terms separately. So we are left with 1 over 2 here, and we are left with 1 over 2x here. When we divide x squared by 6x squared, we are left with 1 by 6. When we divide minus 3x over 6x squared, we are left with minus 1 over 2x. When we divide 2 over 6x squared, we are left with 1 over 3x squared. And this limit was being applied to all the terms, so they can be applied. This limit can be applied to them separately by using the property of limits. So when we applied that, this term doesn't involve x, so it will be 1 by 2. This has x in the denominator. X is very large positive number, so the denominator will be very large, and 1 divided by a very large positive number approaches 0. So 1 by 2 minus 0. Similarly, this 1 by 6 remains same. 1 over 2x is the same. This will approach 0. And 1 over 3x squared also approaches 0, because 3x squared is a very large positive number, and this thing will approach 0. So we are left with 2 plus 1 by 2 plus 1 by 6 up to so on. I haven't written all the terms. This series is continuous. So if we solve these three terms, what do we get? We get 16 over 6 up to so on. So 16 over 6 is basically 2.66, which is pretty close to E. And E is basically 2.7818, and this is almost 2.7. So, and we have written just 4 terms in this series: 1 plus nx plus n into n minus 1 over 2 factorial, x squared plus n into n minus 1 into n minus 2 over 3 factorial, x cubed. So we have only used 4 terms, and still we are getting a result very close to E. If we had written more terms, those numbers would have become even smaller. You can see these terms are getting smaller: 2, 1 by 2, 1 by 6. So that means that the numbers which are being added to 2, they are getting smaller and smaller. So this limit will indeed approach E, and this limit is equal to E. So this is what we needed to prove, that if we take A is equal to 1, our result says that this is equal to E raised to power 1, which is E. So this is true. So now I am taking A is equal to 2 just to prove that that result is true, and nothing changes. We'll apply the same binomial series for this expansion. The only difference will be that our second term is 2 over x now, not 1 over x. So 1 over x will be replaced by 2 over x, and nothing else changes. Same procedures are done, and when we apply the limit, what we get is after simplifying for the first 4 terms, this is what we get, And when we apply the limit to these terms, the constants, they will not change. Obviously this won't change, this won't change. So 5 and 8 by 6, they don't change. The remaining terms, they approach 0. So we are left with 5 plus 8 by 6. And 5 plus 8 by 6 is 38 over 6, which is 6.33. So this is not close to e squared. This is at a fair distance. E squared is basically 7.39 up and so on. So we need to add more terms for this to approach e squared. And if we do that, if we consider 2 more terms, this becomes 38 over 6 plus 2 over 3 plus 4 over 15, and this is equal to 109 over 15 plus up to so on. And this is equal to 7.2666, which is very close to 7.39, which is e squared. So this is approximately equal to e squared. That means that our result is indeed true, and if our result is true, then the value of our given limit is e raised to power 4.